Let's examine the National Electrical Code requirements related to transformer wiring, specifically when transformers supply power to panel boards. We will focus on understanding the relevant sections of the NEC and how they apply to a specific installation scenario. There are two code sections to consider: 240.21c2 and 241.21c6. Section 240.21c2 generally addresses the overcurrent protection of transformer secondary conductors. It states that the overcurrent protection on the primary side of the transformer must not exceed 125% of the secondary conductor ampacity. This rule is designed to protect the secondary conductors from overloads and short circuits. However, this particular section doesn't always apply when the transformer serves a single panel board. Section 241.21c6 provides specific rules for transformers that supply power to a single panel board. This section allows for a different approach to overcurrent protection under certain conditions. According to 241.21c6, for transformers with a capacity of less than 100 kVA that serve a single panel board, the primary overcurrent protective device can be rated at not more than 125% of the transformer's nameplate current rating. This exception acknowledges that the panel board's main breaker provides additional overcurrent protection for the secondary conductors. Now let's consider a practical example. Suppose there's a 150 kVA transformer feeding a single panel board. The transformer's primary is protected by a 90 amp circuit breaker, and the secondary terminates in a 400 amp circuit breaker within the panel board. The question is whether this installation complies with the NEC. Firstly, we need to calculate the primary current of the transformer. To do this, we divide the transformer's kVA rating by the primary voltage and then multiply by 1000 to convert kVA to volt amps. Assuming a 480 volt primary, the calculation is 150 kVA multiplied by 1000 divided by 480 volts, which equals 312.5 amps. However, since we're dealing with the overcurrent protection, we focus on the transformer's nameplate rating. If the question mentioned the primary current nameplate rating, use that to determine 125%. Secondly, we need to check if the primary overcurrent protection adheres to the limits outlined in 241.21c6. Even though the transformer is rated at 150 kVA, exceeding the 100 kVA limit mentioned in 241.21c6, we must consider if it falls under the exception. If it did, the primary protection could be rated up to 125% of the transformer's rated primary current. In the context of the provided information, the primary protection is a 90 amp circuit breaker. 241.21c6 compliance hinges on the actual primary current rating of the 150 kVA transformer. If 90 amps is not more than 125% of the transformer nameplate rating, then it aligns with this section, assuming the nameplate is 72 amps or higher. Thirdly, it's essential to ensure that the secondary conductors are adequately sized and protected. The 400 amp circuit breaker in the panel board serves as the main overcurrent protection device for the secondary conductors. The conductors must have an ampacity equal to or greater than the rating of this breaker. If the secondary conductors are 500 kcmil copper, it is important to verify that their ampacity is sufficient for the 400 amp breaker based on the appropriate temperature rating and installation conditions. Furthermore, the length of the conductors between the transformer and the panel board is a crucial factor. The NEC includes specific rules for tap conductors, which are conductors that are tapped from a larger feeder. If the conductor length is 25 feet, it must comply with the tap rules outlined in 240.21c. These rules stipulate requirements for conductor ampacity, overcurrent protection, and installation methods. Now let's consider the inspector's perspective. The inspector cited 240.21c2, which generally requires the primary protection to be rated not more than 125% of the secondary conductor ampacity. However, This rule doesn't apply in situations where 241.21c6 is applicable, meaning transformers feeding a single panel board. Therefore, if the installation meets the requirements of 241.21c6, the inspector's citation may not be justified. In summary, to determine compliance, firstly, verify that the transformer is indeed supplying power to a single panel board. Secondly, confirm that the primary overcurrent protection is rated correctly according to 241.21c6, if applicable. And thirdly, ensure that the secondary conductors are adequately sized and protected, and that any tap conductors comply with the tap rules. If the installation meets these criteria, you can appeal the inspector's citation by providing documentation and explanations that demonstrate compliance with the relevant NEC sections. The NEC also addresses conductor ampacity based on temperature ratings. Conductors are typically rated for 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. The ampacity of a conductor is determined by the temperature rating of the terminations, the temperature rating of the equipment to which it is connected, and the ambient temperature in which the conductor is installed. It is important to select conductors with an ampacity that is sufficient for the load they will carry, taking into account the temperature dating factors specified in the NEC. In addition to overcurrent protection and conductor ampacity, the NEC also includes requirements for grounding and bonding. Grounding is the process of connecting electrical equipment to the earth, which helps to protect against electric shock. Bonding is the process of connecting different metal parts of the electrical system together, which helps to create a low impedance path for fault current. The NEC specifies the types of grounding and bonding conductors that must be used, as well as the methods for installing them. Furthermore, the NEC includes requirements for working space around electrical equipment. Sufficient working space is necessary to allow electricians to safely install, maintain, and repair electrical equipment. The NEC specifies the minimum dimensions of the working space, as well as the requirements for lighting and access. Moreover, the NEC addresses the installation of transformers in various locations. Transformers must be installed in accordance with the NEC requirements for clearances, ventilation, and protection from physical damage. The NEC also includes specific rules for the installation of transformers in hazardous locations, such as areas where flammable materials are present. It's also worth noting that the NEC is not a static document. It is updated every 3 years to reflect changes in technology and industry practices. It is important for electricians and electrical contractors to stay up to date on the latest edition of the NEC in order to ensure that their work complies with the current code requirements. In cases where there are disagreements or differing interpretations of the NEC, it is often helpful to consult with a qualified electrical engineer or a code expert. These professionals can provide guidance on the correct application of the code and help to resolve any disputes. Furthermore, it's important to maintain detailed records of all electrical work, including permits, inspections, and documentation of code compliance. These records can be valuable in the event of a future inspection or audit. The NEC also addresses the use of surge protective devices, or SPDs. SPD are devices that are designed to protect electrical equipment from voltage surges, such as those caused by lightning or utility switching. The NEC specifies the types of SPD that must be used, as well as the locations where they must be installed. The NEC also includes requirements for the installation of fire alarm systems. Fire alarm systems are designed to detect fires and alert occupants of a building. The NEC specifies the types of fire alarm systems that must be used, as well as the requirements for their installation, testing, and maintenance. The NEC also addresses the installation of emergency power systems. Emergency power systems are designed to provide backup power to essential equipment during a power outage. The NEC specifies the types of emergency power systems that must be used, as well as the requirements for their installation, testing, and maintenance. The NEC also includes requirements for the installation of renewable energy systems, such as solar photovoltaic systems and wind turbines. The NEC specifies the types of renewable energy systems that must be used, as well as the requirements for their installation, grounding, and interconnection with the utility grid. In addition to the NEC, there may be other applicable codes and standards that must be followed. These may include local building codes, state electrical codes, and industry standards. It is important to be familiar with all of the applicable codes and standards in order to ensure that electrical work is performed safely and in compliance with all applicable requirements. Let's delve deeper into the specifics of transformer overcurrent protection as outlined in the NEC. The primary function of overcurrent protection is to safeguard the transformer itself and the connected conductors from damage caused by excessive current flow due to overloads or short circuits. Overcurrent protection devices, such as circuit breakers or fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. The NEC provides specific guidelines for selecting and installing overcurrent protection devices for transformers. These guidelines take into account the transformer's kVA rating, primary and secondary voltages, and the type of load being served. When selecting an overcurrent protection device, it is important to consider the transformer's inrush current. Inrush current is the high surge of current that occurs when a transformer is initially energized. The overcurrent protection device must be able to withstand this inrush current without tripping or opening. The NEC allows for the use of time delay fuses or circuit breakers with adjustable trip settings to accommodate inrush current. In addition to protecting the transformer, overcurrent protection also protects the conductors that connect the transformer to the electrical system. The conductors must be sized to carry the transformer's rated current, and the overcurrent protection device must be sized to protect the conductors from overload. The NEC provides tables that specify the allowable ampacities of conductors based on their size, insulation type, and installation conditions. It is important to select conductors with an ampacity that is equal to or greater than the transformer's rated current and to protect them with an overcurrent protection device that is sized appropriately. Let's also consider the impact of transformer impedance on overcurrent protection. Transformer impedance is a measure of the transformer's opposition to the flow of alternating current. Transformers with higher impedance values tend to limit fault currents, which can make it easier to coordinate overcurrent protection devices. The NEC requires that the transformer's impedance be taken into account when selecting overcurrent protection devices. The impedance value is typically provided on the transformer's nameplate. Furthermore, the NEC addresses the use of coordinating overcurrent protection devices in electrical systems. Coordination is the process of selecting and setting overcurrent protection devices so that the device closest to the fault opens first, minimizing the extent of the outage. The NEC provides guidelines for coordinating overcurrent protection devices in transformer circuits to ensure that the system operates safely and reliably. We should also touch on the topic of transformer grounding. Grounding is the process of connecting the transformer's neutral point to the earth. Grounding helps to stabilize the voltage and provides a path for fault currents to flow back to the source, which can help to trip overcurrent protection devices and prevent electrical shock. The NEC specifies the methods for grounding transformers, including the use of grounding electrodes and grounding conductors. The grounding system must be designed and installed in accordance with the NEC requirements to ensure that it is effective in protecting against electrical hazards. In addition to grounding, bonding is also an important aspect of transformer installations. Bonding is the process of connecting different metal parts of the electrical system together to create a low impedance path for fault current. Bonding helps to minimize voltage differences between metal parts, which can reduce the risk of electrical shock. The NEC specifies the methods for bonding transformers, including the use of bonding jumpers and bonding conductors. The bonding system must be designed and installed in accordance with the NEC requirements to ensure that it is effective in protecting against electrical hazards. Let's also discuss the importance of proper transformer ventilation. Transformers generate heat during operation, and it is important to provide adequate ventilation to prevent overheating. Overheating can damage the transformer's insulation and reduce its lifespan. The NEC specifies the requirements for transformer ventilation, including the minimum clearances around the transformer and the use of ventilation openings or fans. The ventilation system must be designed to dissipate heat effectively and maintain the transformer's operating temperature within its rated limits. Another crucial aspect of transformer installations is proper labeling and signage. The NEC requires that transformers be labeled with their kVA rating, primary and secondary voltages, impedance, and other important information. This labeling helps electricians and other qualified personnel to identify the transformer and understand its operating characteristics. In addition to labeling, the NEC also requires that warning signs be posted near transformers to alert personnel to potential hazards such as high voltage and the risk of electric shock. The warning signs must be clearly visible and legible. Let's also consider the impact of harmonics on transformer installations. Harmonics are distortions in the alternating current waveform that can be caused by nonlinear loads such as electronic equipment. Harmonics can cause transformers to overheat and operate inefficiently. The NEC addresses the issue of harmonics and provides guidelines for mitigating their effects, such as the use of harmonic filters and reactors. It is important to consider the potential for harmonics when designing and installing transformer systems. Furthermore, the NEC addresses the use of autotransformers. Autotransformers are transformers that have a single winding that serves as both the primary and secondary winding. Autotransformers are typically smaller and less expensive than traditional two-winding transformers, but they also have some limitations. The NEC specifies the requirements for installing autotransformers, including the need for special overcurrent protection and grounding. In addition to the technical aspects of transformer installations, it is also important to consider the safety aspects. Transformers can be dangerous if they are not installed and maintained properly. It is important to follow all applicable safety procedures when working with transformers, including wearing appropriate personal protective equipment such as gloves and safety glasses, and energizing the transformer before performing any maintenance or repairs. Let's delve into the specifics of conductor ampacity and how it relates to transformer installations. Conductor ampacity is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables that specify the allowable ampacities of conductors based on their size, insulation type, and installation conditions. When selecting conductors for transformer installations, it is important to choose conductors with an ampacity that is sufficient for the load they will carry. The load current is determined by the transformer's kVA rating and voltage. The NEC also includes requirements for directing conductor ampacities under certain conditions. For example, conductors that are installed in raceways or cable trays with other conductors may need to be derated to account for the increased heat buildup. The derating factors are specified in the NEC tables. In addition to derating for ambient temperature, conductors may also need to be derated for voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to operate inefficiently or malfunction. The NEC recommends that voltage drop be limited to a maximum of 3% for feeders and 5% for branch circuits. To minimize voltage drop, it is important to select conductors with a large enough size and to keep the conductor runs as short as possible. Let's also discuss the importance of proper conductor terminations. Conductor terminations are the points where conductors are connected to equipment such as circuit breakers, transformers, and panel boards. Proper conductor terminations are essential for ensuring a safe and reliable electrical system. The NEC specifies the requirements for conductor terminations, including the use of approved connectors and proper torquing procedures. The use for corroded conductor terminations can cause overheating, arcing, and even fires. It is important to inspect conductor terminations regularly and to tighten or replace them as needed. Furthermore, the NEC addresses the use of flexible cords and cables. Flexible cords and cables are used to connect portable equipment to the electrical system. The NEC specifies the types of flexible cords and cables that are permitted for various applications, as well as the requirements for their installation and use. Flexible cords and cables must be protected from physical damage and must not be used as a substitute for permanent wiring. Let's also consider the impact of environmental factors on conductor installations. Environmental factors such as temperature, moisture, and corrosive chemicals can affect the performance and lifespan of conductors. The NEC specifies the types of conductors that are suitable for various environmental conditions. For example, conductors that are installed in wet locations must be listed for wet locations. Similarly, conductors that are exposed to corrosive chemicals must be made of materials that are resistant to corrosion. It is important to select conductors that are appropriate for the environmental conditions in which they will be installed. In addition to the NEC, there may be other applicable codes and standards that must be followed when installing conductors. These may include local building codes, state electrical codes, and industry standards. It is important to be familiar with all of the applicable codes and standards in order to ensure that conductor installations are performed safely and in compliance with all applicable requirements. Let's explore the nuances of transformer tap rules within the NEC. Tap rules pertain to situations where conductors are tapped from a larger feeder, and these rules are designed to ensure the safety and reliability of the electrical system. The NEC specifies the requirements for tap conductors, including the minimum ampacity of the tap conductors, the maximum length of the tap conductors, and the overcurrent protection requirements. One of the key requirements for tap conductors is that they must have an ampacity that is at least 1/3 of the ampacity of the feeder conductors from which they are tapped. This requirement helps to prevent the tap conductors from being overloaded. The NEC also specifies the maximum length of tap conductors. The maximum length depends on the ampacity of the tap conductors and the type of overcurrent protection that is provided. In general, tap conductors must be kept as short as possible to minimize voltage drop and to reduce the risk of overload. In addition to the ampacity and length requirements, the NEC also specifies the overcurrent protection requirements for tap conductors. The tap conductors must be protected by an overcurrent protection device that is sized to protect the conductors from overload and short circuit. The overcurrent protection device must be located at the point where the tap conductors connect to the feeder conductors. The NEC provides several exceptions to the tap rules. These exceptions are designed to provide flexibility in certain situations where the standard tap rules may not be practical. However, it is important to carefully review the exceptions to ensure that they are applicable to the specific installation. Let's also discuss the importance of proper documentation for transformer installations. Proper documentation is essential for ensuring that the electrical system is installed and maintained in accordance with the NEC and other applicable codes and standards. Documentation should include detailed drawings of the electrical system, including the location of all transformers, conductors, and overcurrent protection devices. The drawings should also show the size and type of conductors, the ampacity of the overcurrent protection devices, and the grounding and bonding connections. In addition to drawings, the documentation should also include a written description of the electrical system, including the design criteria, the calculations that were used to size the conductors and overcurrent protection devices, and the testing and commissioning procedures. The documentation should be kept in a safe place and should be readily available for future reference. Furthermore, the NEC requires that certain information be permanently marked on electrical equipment, such as transformers and panelboards. This information includes the equipment's voltage rating, current rating, and short-circuit current rating. The markings must be legible and must be located in a conspicuous place. Let's also consider the importance of ongoing maintenance for transformer installations. Regular maintenance is essential for ensuring that the electrical system continues to operate safely and reliably. Maintenance should include visual inspections of the transformers, conductors, and overcurrent protection devices. The inspections should be performed by qualified personnel and should be documented in writing. During the inspections, look for signs of damage, such as cracked insulation, loose connections, and corrosion. Any damaged equipment should be repaired or replaced promptly. In addition to visual inspections, maintenance should also include testing of the overcurrent protection devices. The testing should be performed by qualified personnel using calibrated test equipment. The test results should be documented and compared to the manufacturer's specifications. Any overcurrent protection devices that fail the testing should be replaced immediately. Let's also discuss the importance of training for electricians and other qualified personnel who work on transformer installations. Electrical work can be dangerous if it is not performed properly. It is important to ensure that all personnel who work on transformer installations are properly trained and qualified. Training should include classroom instruction, hands-on experience, and ongoing continuing education. The training should cover the NEC, as well as other applicable codes and standards. It should also cover the safety procedures that must be followed when working on electrical equipment. In addition to formal training, it is also important to provide personnel with access to the latest technical information and resources. This can include technical manuals, industry publications, and online forums. Providing personnel with the information they need to do their job safely and effectively can help to prevent accidents and ensure the reliability of the electrical system. Finally, it is important to remember that the NEC is a living document that is constantly being updated. It is important to stay up to date on the latest changes to the NEC in order to ensure that electrical work is performed in compliance with the current code requirements. There are several ways to stay up to date on the NEC. One way is to attend training courses and seminars that are offered by electrical trade organizations and educational institutions. Another way is to subscribe to industry publications and online forums. By staying informed about the latest changes to the NEC, you can help to ensure that your electrical work is safe and compliant.